file in there, we just put like sys.argb.
Yeah, you would have to call sys.argb. Yeah. Okay, cool. So it's 3 o'clock, so let's get started. So just as a final reminder, assignment 1's due tonight, and you have unlimited submissions, so don't worry if you already submitted and, oh, that was the wrong one. Go ahead and resubmit if you want to. So are there any questions about assignment 1 before tonight? No questions? Okay. So I just wanted to make note of a possible project idea that's not on the list. So how many of you ever heard of NSIDC, the organization? NSIDC. So it's the National Snow and Ice Data Center. So what they do is they collect a lot of information about climate data, about ice data, all that kind of stuff. So one thing that I've looked at in my undergrad thesis was looking at sea ice concentrations of the Arctic Ocean over time. So what they have this really large data set, which corresponds to the concentration of the concentration of ice at various locations in the Arctic and the Antarctic at the North and South Pole. So what you could do here is to see, are there any patterns over time? So you can look at what I've done in my thesis and see what else you can do for that. So that'd be a really nice idea for a project. So if you want to do that project, you can just email me and I can give you more details. Okay? So are there any other questions before we get started back on the material? Okay. All right, so we have been talking a lot about algorithms, right? So algorithms are these procedures where we have this entry and exit point, and they're well defined. There's some procedure that gets from the inputs to the outputs. So you're given inputs and you produce outputs, and there's a step-by-step procedure that allows you to map an input to an output. And so what we wanted to look at was just in terms of algorithm analysis, when we're given a particular problem, how do we phrase this in an algorithmic way and try to analyze it in an easy way? So the first problem that we looked at was looking at this problem of displaying all prime numbers between 2 and 10,000. So what we figured out was we can do this trial by division algorithm to figure out when a number is prime, and then if it is, then we print it, and then do a for loop on each of the numbers between 2 and 10,000 and print the ones that really are prime. So then we talked a lot about trying to structure our programs in a more effective way in terms of analysis. The reason for that is that we can reuse functions so we don't have to reinvent the wheel. We can be more accurate since the functions are shorter, and it's easier to analyze from a algorithmic standpoint, because if you have shorter functions, there's less to analyze for that function, and if it's used somewhere else, you know how long it takes to execute that one line. All right, so we did multiple attempts. So we did a brute force approach. We did another approach by noticing that we're doing a lot of checks that are completely unnecessary, so we eliminated most of those by only going up to the square root of the number. Then we improved on that by not checking every single even number along the way for a divisor, so we effectively cut the search time in half. And then we pretty much just made a program that, well, the program in the slides is different than the one we chose, but the one in the slides is about trying to structure our program so that we have a set of test cases and we test whether the particular input matches the particular output that we want. Okay? And so we can run our program. Then we talked about how to analyze this program, this prime finding program. What we initially thought was that the program ran in O of square root n time, where n is the input that's given to you. But we figured out that algorithm analysis is not done this way. It's done in terms of the size of the input, not the value given. So the input size is log n because in computers we store all integers in binary. So in order to store a number that has value n, we take about log n bits to store that particular number. And so the algorithm runs in square root n time in terms of log n. And so we figured out that's an exponential time algorithm, or just more informally, that's a very inefficient algorithm. And so I proposed this project idea for a paper that was published 14 years ago about how they were able to show that you can, in fact, do polynomial time in terms of log n instead of just n. So, but the important thing is that efficient algorithms are important to find because they're scalable for larger and larger inputs. The amount of time or the amount of space, depending on what we want to figure out, does not increase too much. Because if we have really large input, we don't want it to run too much or use too much space, that sort of thing. So I have this handy guide to figure out how to do efficient algorithms, such as trying to abstract away all details of a particular programming language or edge cases, things like that. So then we finally talked about recurrence relations, which are a way of analyzing a particular program's runtime when it calls itself. So for our prime program, it didn't call itself because we can just look at the for loop and figure out how many times it executes. But here, we could have, we can be calling ourselves, but if we want to figure out the runtime of the entire algorithm, we would need to know the runtime of the recursive calls. But that's kind of like a circular argument. Like if we knew the runtime of calling ourselves, we would know the function's runtime already. So it's a circular argument. So what recurrence relations do and techniques to solve recurrence relations are pretty important. So there's no way to solve one in general. So the best idea is just to guess and then just try to confirm that your guess is correct. There's another method called the master method, and there are more complicated routines, which are I propose as a project idea. So the guessing idea is we're just going to guess a particular runtime. And another way to help you guess is to unravel the recurrence a few times and then just try to see if there's a pattern that appears. So when we did this, which is the recurrence relation for merge sort, we expanded it a few times, and then we conjectured that it had a particular form, and then as an exercise you can verify this. But when we have a base case, which is when we divide this array into two pieces until we get to when we have a one-element list. That's when we stop doing recursive calls, and then we figure out how long that recursion must take, which turns out to be log base 2 of n, because the input length is n, and we divide it into two pieces each time. So it must be log base 2 of n for the height of the recursion. And so if we plug back in, we get a runtime of n log n, which is the runtime of merge sort. And so I gave just an overview of what the master method is. Again, I don't expect you to know the proof of how this works, but it's just knowing a general form for most recurrences. Because most algorithms you'll encounter that do recursions like this have a form of having I have A different subproblems that I'm doing, each of which divides the original problem into into size B, 1 over B each. But the problem is that some recurrences don't divide evenly or not the same recurrence each. So the master method won't apply here. So you'll need to research some other techniques to solve these recurrences. Okay, so any questions about any of that so far? Okay, so to get back to the material, so let's look at one more problem that we finished up, that we started last time. So suppose we're clairvoyant, right? If I'm clairvoyant, I'd be going on the New York Stock Exchange and doing stocks instead of doing this, but actually I might still be doing this, but it'd be nice to know, if we knew all stock prices in the future, when to buy and sell stocks, right? Because I want to maximize how much money I get. So what we figured out was the optimal way to buy and sell stocks was to buy when the stock price is lowest and buy when and to sell when it's highest. So it's the maximum sum over that when I buy and when I sell. So when should we buy and sell? The good idea, buy when it's lowest, sell when it's highest. So well, you may think, well, when the value of the stock is pretty much always positive, right? So when is the best time to buy and sell a stock? Well, it's just to buy at the beginning and sell at the end, right? So if we model this problem in terms of the change in the stock day to day, if the stock change is always positive, so it's always increasing, then the best time is to buy at the start and sell at the end, right? Because it's always going up, right? But that's not very interesting. What I think is more interesting is when the stock does lose money, right? So there's a negative amount from a day to day. So it's more important to figure out when is the best time to buy and to sell, when we may have some decreasing part in the list of how much the stock changes day to day, right? So an equivalent formulation of this is basically we will look at the change in the stock price day to day. So the first element will be, say, the amount that, starting from 0, we'll just say the stock is at 0 right now, and we'll say maybe it rises $10 the first day. So the first element will be 10. Then maybe it falls 5 the second day. So we'll say that the second element is 5, right? So what we want to do is, since buying a stock and then selling it later is contiguous, so given this list of integers, I want to find a contiguous sublist such that the sum of all of those elements is maximum. Okay, so that's the problem I want to do. If the elements are all positive, just take the entire list. What if all the elements were negative? If every single element is negative, don't buy the stock, right? Yeah, so, and there are actually some versions of the problem where you have to have a non-empty choice. So if I had to have a non-empty choice and all the elements were negative, what would be the best idea?
Find the least negative value?
The largest value.
Largest negative.
Yeah.
Smallest.
The smallest negative.
Largest negative?
Yeah, largest negative. It depends on how you're thinking of it, right? But like the largest integer is completely unambiguous, right? Cool. So what's a brute force idea? So what we came up with last time is, could there be an exponential number? Could we have an algorithm that runs just as long as our prime finder algorithm? Well, what we figured out was that we must have a contiguous sublist, right? Because that's what we want to find. We want to find the maximal contiguous sublist. So how many possible contiguous sublists could there be? Well, there's a start date and an end date. So, and obviously the end date has to be after the start date. That's just obviously true. Because I'm not a time traveler, right? So how many possible of these contiguous sublists could there be? Well, I must choose a start date and I must choose an end date. So how many of those are there? Well, is n, choose 2. From n items, choose 2 out of there, and I must guarantee that they're not the same. Because I'm going under the formulation that it's a non-empty list. So if we choose 2 distinct dates, one is the start date, one is the end date, and what we do is we look at each of these possible contiguous sublists and record the sum for each of them. Right? So let's just say that the start date is the second day and the end date is the 5th day. Then I record that the sum from the 2nd to the 5th day, I record it in some table or something. And then at the end, when I have brute forced every single possible start and end date, I find the one that has the highest sum. Okay? So how many possibilities are there? Well, we choose 2 dates out of n possible dates, so therefore we have O of n squared. There are some constants that are hidden there, but it's asymptotically about n squared. We want to sum the elements in each one. So the size of each one, well, there are some sublists that start from the very first date and go all the way to the very last date, but there are some that are very short, right? There are some that are only 1 day long, or maybe 2 days long. So what is the average of those? Is n over 2, right? I have some that are really long and some that are really short. So the average is about n over 2, which is O of n hiding a constant. So if we have n squared different subproblems that I want to solve, and each one takes O of n time, I have a cubic time algorithm, right? N squared times n is O of n cubed. Can we do better? There's actually, if we even analyze the algorithm better, we can get a smaller constant that's hidden in the O notation, but it'll still be asymptotically n cubed. And there are some algorithms, not this one, but there are some algorithms that, given just a better analysis, you can get a better runtime asymptotically, which is quite cool. But here it's n cubed, even with better analysis. You can actually do better with divide and conquer, which will be a topic after in a few days, I would think. But so we can get, I think, down to n squared. But for now, we're just going to deal with an n cubed time algorithm. So I coded this problem up in Python. So what I wanted to do was I wanted to just generate a random list of integers because I don't have a source for stock price changes day to day. So I just thought, let's just make a random list, right? So what this random list is calling random.randint. So we haven't seen this function, but I bet you can figure out that it's just calling a random source for giving me a random integer. And what do you think these two arguments are trying to give me? Bounds, right? So this will return to me an integer between negative m inclusive, m exclusive. And so we actually haven't really seen this notation. So how many of you know what this notation is when I write the for loop inside the square brackets? What do you think that's trying to do?
Does it return a list?
Yeah, it is returning a list, but I'm doing it in place, right? I'm not making like one list and doing a for loop, then appending to that list. I'm doing it all in one time. So how long, so what do you think this is called? Doing this all at once? It's a list expression, right? So I'm doing, actually it's called list comprehension is the formal term in Python. So I'm making a list in place by saying for I in this range, return the thing on the left of the for state of the for loop. So it's basically it's going to return the element this particular call n times because that's how many times I'm doing my for loop. So it'll give to me an n element list, each of which is an integer between minus m and m minus 1 because it's exclusive. So the main function here is just going to take a length of this this list that I want to analyze, the range, which will be the minus m to m minus 1 thing, and then so L I'm going to call to be a random list, and so what m is going to be is the sum of the maximal sublist so far. I have current max list here, but I'm not actually doing anything with it yet. So what I'm going to do is I'm going to choose my I and j. So I is going to be the start of the contiguous sublist, and j is going to be the end. So what I is going to do is it can be anywhere from the start to the end. But what can the end of the list be? Only. It can only be from where? Yeah, so it can only be from I plus 1 up to the end. Right, so I can be anywhere, but j has to be from where I is at least to the length of the list. And so what I'm just calling here is whatever m was, just return the max of what it was before and what this sum is right now. Okay, so m is just basically going to be I'm going to keep track of the sum itself over time. And then at the end, I'm just going to print it. All right, so no, I don't want to purchase. So let's run Python 3, and what did I call it? Stocks. Oh, so what was my error there?
Index out of bounds.
Right, index out of bounds. So it was expecting that I needed to give a length and a range, right? So let's just say that my list length is 100, and the bounds actually don't matter, but it's just good to be able to allow the user to put it in. So let's just say 2,000. So my list is going to have 100 things in it, and it's going to be a random integer between -2,000 and 1999 because it's exclusive. Right? So it found it pretty quickly. So the maximum array sum was 8,000. So if I ran that again, it's going to give possibly a different number, right? Because it's random every time. So if I run this for a list that is 10 times longer, how long, on average, do you think this algorithm will run longer than the previous time? Because it's 10 times longer. So what's the runtime asymptotically of my algorithm? N cubed, right? So what is 10 times longer cubed? 1,000. So we expect it to run about 1,000 times longer. So it actually ran a lot longer, right? And I doubt you want me to do 10,000 because that'll run for the rest of class, I would conjecture. Okay, cool. So any questions on what this implementation does? Okay, cool. All right. So we covered this stock. So we looked at this brute force idea, try to every single possibility, and then keep track of the one that we want. Keep track of the maximum over time. And so it seems like there is some kind of mechanism behind brute force, right? There's some algorithmic properties of brute force. So what does brute force really mean in general? Try every single possibility, right? So I thought this was cute. I don't know how to solve problems, but when I do, I brute force. Yeah. And actually, how many of you heard of an adversarial argument? So what that is basically, for some problems, an adversarial argument is basically there's an adversary trying to make you fail at trying to solve a problem, right? So you're trying to solve a problem, and it's just giving you bad examples over and over and over. So what it's trying to do is trying to make your algorithm run as long as possible. So in some problems, an adversarial argument says that you can't do better than brute force. So one example of that would be in an unsorted list, find a particular integer. So like you have a list of size n, and you're given an integer, want to find the integer in the list. So an adversarial argument would say, I'm going to give you the first integer is not going to be your integer. Second integer is not going to be that integer. And it's going to force you to go all the way to the end of the list before you find your integer. So there's no way to be able to search that list faster than just searching every single thing, right? So an adversarial argument actually will force you to do brute force sometimes. But for some problems you can do better, but sometimes you can't. So brute force, just in general, just try every single possibility that you can, right? And when we test each one, if it succeeds, we say yes. If it doesn't work, we say no. Pretty simple. So this is just pseudocode for, in general, we're given a particular problem, and I want to brute force a solution, right? So, or at least get all possible solutions. Like for our prime example, we want to print every single integer, right? So I'm returning every single integer that's prime between a start and an end. So in that case, it was 2 and 10,000. So here, let f, I'm going to call it to be the set of all possible candidates with all possible values. So f is basically brute forcing every single possible answer to this problem that there possibly could be, right? So this could be this can actually be an infinite sized list in some cases, but so we can't deal with it all the time. And obviously in some problems this could be a very large set. But if I wanted to do brute force, this is just a way to do it. Find the set of all possible candidates, then we iterate through each one, and what I'm going to call S is going to be the set of candidates which do solve the problem. So for every single solution, C here means candidate. So for every candidate in this list of possible solutions to the problem. If C is a solution to the problem, which we can just verify by testing a procedure on the problem, then we add the particular candidate to this set of solutions that I'm currently storing, and then return the set. Okay? So, like for our prime problem, it's basically F is the set of integers from 2 to 10,000, right? Those are every single possible thing that could possibly be a prime value. And so what I'm doing is I'm iterating through every single element in that list. If C is a solution to P, what that was that prime checker part. It was checking whether each of those integer candidates was a solution to P. Then we add the candidate if it was a solution. Okay. But the thing is, instead of just many solutions, maybe I just want one solution, right? In some contexts, this list, as I said, it could be infinitely large, right? Maybe like if you wanted to print every single prime number, that's an infinite size list, right? Because you need to check every single integer. But maybe I just want one prime number, which will be much more efficient. So how do we do that? Well, I want to define a procedure, brute force one solution for this problem P. So we do the same thing again. And since I said that this is an infinite size list, what we could do instead is do the Python way, which is instead of giving the entire list all at once, just generate a new solution every single time. And we can make sure that we don't generate a previous solution. So what we can do here is do that generator solution and then just generate the set of all candidates and then loop through that list. If C is a solution, then we can just return C, right? Because I don't care what solution I want, I just return one of them. So then I can just return true or return C or something like that. And return false if we've iterated through the entire thing and we never found a solution, right? Because if we never found a solution, then we can't return a solution, obviously. Okay? What if we can't store all possible solutions at once? As I said, we can generate one at a time. So we can have F and S be both the empty set. So S is going to be this set of solutions as before. But F is we're going to be generating solutions one at a time. So like while there's still a solution to generate, C, I'm going to generate a new solution and add it to F, right? And so when we call this new unique solution, we'll check if F already generated it, right? Instead of making this entire list all at once, we just check if it's an F already. And if it's not, then we make a new one. If it is a solution, then we add it to the set of solutions as we did before, and then return. Okay? So are there any questions on all of the algorithm stuff? I know that was a lot to take in. Okay. So just analysis of brute force. Sometimes we can't actually do brute force of all solutions because sometimes you may have the problem of you have too many possible solutions to generate, which is definitely possible. Another one is maybe you do have a few number of solutions, but even generating a solution takes a long time or a lot of space or something like that. So sometimes it's just infeasible to do this. The solution space may be too large, generating solutions difficult. In that one example where we checked that that the C solution is not an F already, it may be difficult to even search through this list because this list could be very large, like to see if this solution has already been made. So even that might be difficult. Even checking a solution is difficult. There are some problems that even checking the solution is difficult to do, and even if you even if generating solutions is easy, even checking it might be hard to do. So since this the algorithm for stocks runs an n-cubed time, the total possible candidates for start and end dates with the sum can be for an array of size 1,000 is just 1,000 cubed. So 1,000 squared is 1,000,000. So 1,000 cubed is 1 billion. So that's 1 billion candidates that I'm testing for something only of size 1,000. And obviously, 1,000 size element list at this point you should know is not a very large list, right? So even for much larger lists, this could be very prohibitive to do. So that's why we turn to other algorithmic techniques like divide and conquer, which we'll see maybe Thursday. And then like dynamic programming, which is about storing previous computation and not doing computations over. Some techniques like optimization. So what you do there is you, instead of looking through all possible candidates or storing previous computation, you may not get the absolute optimal answer, but you will be approaching the optimal answer. Okay, so that's the whole point of optimization. All right, so we can only use this really for small problems because it's an n-cubed time algorithm. All right, so let's go to the next topic, which is backtracking. So when we were talking about brute force, we're talking about generating all possible solutions, right? We're just generate all possible solutions and look at each one and see if it was a solution. Then if it is a solution, then we add it to a list of solutions, right? So that doesn't seem like a very good structured way to look through all possible solutions. And as I said, you may have to look through all possible solutions. But it'd be nice to have some properties of looking through all possible solutions, but more in a more structured way. So that's what backtracking and constraint satisfaction is all about. So there are many possibilities for a solution to a problem. And one of the problems with generating all solutions is that we may not even know how to generate all solutions. It may be very difficult to, maybe even conceptually or time-wise or something else, to even generate even one solution, let alone many solutions. So what we can do is we can start in a start configuration, just pick a random start configuration, and then we try all possibilities one by one. And then what we do there is we look at all possible solutions that I could assign at this given point, right? At this start configuration, I look at what I can do right now, and then I recursively call on myself. If I get to a point in the recursion when I get to saying that I have some setting to some values in my problem, and I get to a point where I can't assign anything else to any other unsigned value, then I must backtrack. I must go up one level in the recursion, right? Because what I've assigned so far couldn't have worked, right? Because I couldn't have assigned anything else to the other unassigned values. So that's the whole idea behind backtracking. So we try all the possibilities that I can do in one step, then I recursively call myself. And then if I ever get back to a point where I have another value to try, I try that value, then I recurse again. Okay? So basically, I will be trying all possible values, but it's more structured, right? Because I try every single possibility, and I'm effectively removing all the bad solutions just by recursing up, not actually generating those solutions. So if a solution's reached, right, because if I assign all the values and it actually is a solution, then I just stop, right? Because I found a solution. If we reach a point where we can't recurse further by assigning a value, then I must stop there and return to where I was before. I must go one level up in the recursion. So as an example here, we have a maze, and so the goal of this, maybe I have it here, yeah. So the goal of this maze is I want to find a path from the upper left white cell to the upper right white cell. So there's, as you can see, there are some ways that you'll get stuck. So like if we go down from the second cell over all the way down, we will get stuck. So the start configuration for this problem is, maybe I have it here, yeah. So the start configuration is the start cell, right? That's my start configuration. And so my next configuration is, what are my possible moves that I can do from that start cell? Well, the only one is to move right one cell to the second cell, right? So there's only one possibility, so I do that possibility, and then I recurse on that. So now I'm at the second cell, right? And so I have a choice. I can either go continue right, or I can go down this path. So I'm doing a backtracking algorithm. So I'm just going to try each one of them. So maybe I choose the down way first. So I recurse going down, and then I go down, 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 and then I reach the bottom of that tunnel, I guess. I reach down there, and then when I get all the way down, I see I can't move anywhere, right? And so, since I can't move anywhere, I must backtrack to the place right above me. And then it said, well, the only way I could have moved was down one cell, and I don't have anything else. So I'm done checking at where I am, and I didn't reach a solution, so I must backtrack again. And we keep backtracking, back, all the way up to the top. And it said, well, going down was not the right way. It's because I didn't generate a solution. So I must try the next one, which is moving right here. Okay? So here, we're going to first try moving down. Eventually, we'll get to a point where we can't go any further. So we return to the parent and then try the next solution, which is right in this case. So we try moving right and recursively call until we get to the goal state. So obviously, if there is no way to get to the goal state, which is this upper right corner, then I won't find it this way, right? Because I'm trying every way from the start state. If there's no way to get to the final state, I won't generate it. But if there is a way to get there, I will find it, right? Because it will try every possible way through the maze until I can generate a solution. Okay? Yeah. If there are more than one what? Yeah, it'll. If I'm concerned about if there's a way to get any one of the goal states, then it'll work, right? Because it'll get to one of them for sure, if there is a path at all. So yeah, so if there are more than one goal state, you'll definitely get to one. Yeah. You can keep track of that, but you don't really have to. You just need to keep track of what moves I can do at any given point, right? Because that's all I really need to know. Is if I can move left and move down, then if I try the left one and it says no, I can't go that way, then I must try going down. And if both of them say no, then therefore I must go up, because there's nothing else I could do anyway. So I must go up. Okay? Does that answer your question? Yeah. Any other questions about that? Okay. So actually the order does not matter here, because I could either try going right or going down. I'm not concerned about efficiency really here. What I'm concerned about is trying all possibilities in a more structured way. All right, so we'll turn now to a really cool problem called the 8 queens problem. So how many of you have heard of 8 queens? All right, so the idea about this is, how many of you play chess? So you all know about queens, right? So the queen placed on the board can move as far as she wants in any of the 8 directions. So the 4 cardinal directions, as well as the 4 diagonal directions, as far as the board is. And we know that the chessboard is 8 by 8 squares. And so our goal here is to place 8 queens on the board in some positions such that none of them can attack any other queen. So obviously I can't put them all on the main diagonal, right? Because each of them can attack each other by going along the diagonal. But one technique you can do is you can go 2 spaces over and 1 down, because that's not one of the 8 directions. So you can try that way, but what I want to do is use a backtracking algorithm to solve this problem. Okay. So no 2 queens in the same row, column or diagonal is another way to say the same thing. So what's the total number of possibilities here? Well, how many squares do I have? 64, right? And so once I place a queen somewhere, how many do I have? 63, because I can't place in the same square. So that's basically 64, choose 8, right? So, and that's just this expression, which evaluates to about 4 billion possibilities. So the problem with this is that even if we're checking 1 million which is actually a very high number. Even if we do that, then it'll take a very long time to even check if there is a solution. We don't even know if there is one. There is, but there are actually very many of them. It'll be hard to even check if there is a solution at all here. So the problem is that what does this take into account? Well, it takes into account the ones on the main diagonal. It takes ones on the other diagonal. All 8 queens in each of the 8 rows, 8 columns. It includes a lot of ones which we think, why would you ever check that, right? There's no point in generating that solution. So doing it this way will generate a lot of solutions that just flat out won't work. So using backtracking, we will generate 4.4 billion solutions, but what we want to do is generate smart solutions. And that's what constraint satisfaction, the second part of the title, is all about. So it'll include many solutions for which we don't want them. So is there a more strategic way to do it? And so what we'll call a square is conflicting. If we place a queen there, then it'll be able to be attacked by or attack another queen somewhere else. So it'll have a queen in the same one of the 8 directions. And so what I want to do is just start with a candidate solution, right? Which is just placing a queen right at the start. Okay? You can pick any square you want, but I'm just picking the start square to start with. I could pick, so I have 64 different possibilities I can choose here. Then no queen can be placed in the, I'm going to do a figure of this in a second, but no queen can be placed in the same row, column, or diagonal. So this is what the constraint satisfaction is. So when I place that queen in the first space, I've removed every single possibility in the first row, column, or diagonal. I've removed all those squares. No queen can be placed there, right? Because if I did, then it would be a conflicting square. And so we move to the first non-conflicting square by scanning right until we find the non-conflicting square, then place the queen there, then we recurse. So we are going to generate a lot of solutions here, but we're being smart about it. We're generating only the solutions that we know are possibly going to work. We're removing all the squares for which we know will not work. Okay? If we ever get to a point where if there are no non-conflicting squares at this point after until the end, then I can't place a queen, right? So therefore, all the other queens are in some wrong position, so I backtrack, as we did before. So I have this nifty little diagram. So what I'm going to do is I'm going to place the queen in the first square. And so what these arrows represent are I can't place a queen there. Okay, so I've removed the first row, obviously where the queen is, the column, and the main diagonal. So what is the first non-conflicting square here? Well, it can't be the first row, obviously. Can't be the first element in the second row. Can't be the second element in the second row. So the third one will work, so let's put it there. So let's place a queen there. And note, since if we place a queen there, I must check every single one of the 8 directions. So now I've removed a lot more squares this way. So now I want to place another queen. So what's the next non-conflicting square? It's the one that's 2 over and 1 down, yeah. So if we place one there, then we eliminated more squares. So the next non-conflicting square will be on the 4th row, 2nd column. So actually, yeah. I don't know why I didn't see that. I spent a long time making the slides. And I handmade each one of these. And anyway, yeah. So it actually turns out if you place in that second square, it won't work. But that's so unfortunate. So let's just say that we place the queen there because it actually doesn't matter where I place the queen, right? Because I can place it in any non-conflicting square because I could be checking every single non-conflicting square possibility for a given configuration here. So I could be checking this one. So I remove those squares, then I place here, then I place here, then I place here. So now I've placed 7 queens, and now since there are no non-conflicting squares anywhere on the board, I can't place the 8th queen, right? I can't place a queen. It must be in the 8th row, right? Because if it were in any other row, it would be on the same row. So I can't place anything on the 8th row, so I must backtrack. Well, here I don't have any other non-conflicting squares in this row, so I'm working non-conflicting squares per row. So this is the only one for this row. If we back up even more, then we notice that there are none there. So we must backtrack again. So we have this one here. If we remove that queen, then the next non-conflicting square is the one that's 2 spaces over, right? So then we try to place one there, and then we keep trying again until we eventually get a solution or we find that there are no solutions at all, okay? And so just as for completeness, this is an example solution of an 8 queens solution. It turns out that there are, I believe, 92 for an 8x8 grid, and it just goes exponentially up after that. So there are tons of solutions to this, but here's an example one. Okay, so any other questions before we take a break? Okay, let's take a break. We're back. So I wanted to answer any questions about the project, if you've seen any of the topics in the project, if there's any concerns, anything like that. So
we can work as a group.
I limit the group size to 3, but and obviously if you're working with someone, you're going to be expected to do more than if you work by yourself, but you can definitely work in.
Are you going to define what you mean by or?
Well, an individual effort is obviously 20 hours. That's what I expect from a project that's worth this much in the class. But so if you worked in a group of 3 people, it's obviously wrong to just say, I expect 60 hours of work, right? Because there's coordination among the team members and stuff like that. But it's just, if I see that you've actually dug deep into this one particular algorithm, then it's fine. I'm not going to work like on a rubric. I'm not going to be super strict on things. It's just, if I see the effort, then the grade that you get will be a reward for that. Okay. Any other questions about the project?
So if there's a whole list.
Mm-hmm.
So if say I pick one project, does that mean nobody else can pick that up?
I prefer that, but because I'm hoping we can get through the material quick enough so that we have presentations at the end. And it might be a good idea if you do pick up, end up doing the same topic as someone else, then you work together as a group for that. And obviously there are 21 projects here, and any other project you might want to do. So, and there's only 9 of you. So I would think that there shouldn't be any problems here, but if there is, send an email to me. Okay? Any other questions about this?
Actually, I got one more
Yeah.
question about the minimization.
Uh-huh.
So, does it matter how long the program actually takes?
Nope.
Okay. Just minimize.
Yep.
Doesn't matter.
It's only bytes that I care about. So that's an application of caring about the space that you use instead of the time.
Yeah.
Right? And so sometimes we do care about space instead of time. So, yeah. So only the amount of time it takes. Only the amount of space that it takes is.
Basically, as long as it runs and it's under XYZ for bytes.
Don't make my machine run for a couple days before I get the answer. Yeah, but as long as it's reasonable. So, how many of you? I talked about this. How many of you know HackerRank? So, yeah, if any of you don't know, so HackerRank is basically they have a bunch of problems on there for which you can write in any programming language you want, and you solve a particular problem by just submitting your code and they run your code, right? So what they do is for very large inputs, what they do is, well, actually for all inputs, they limit the amount of time for your program to run. So like for Python, for example, they limit to 10 seconds for a given input and output. And so even like for assignment 2, where I give you the Project Euler problems, they have Project Euler problems on there, but they make it so that the inputs are so large that you'll need to think more creatively about how to program your solution. So even if your solution's correct, it'll take a long time. So in that case, do care about time, but here we only care about space. So any other questions about anything? Okay, so yeah, make sure to send in your proposal by June 6th, which is 2 weeks from 2 days ago. Okay? Yeah. And also who you're working with if you're working with somebody. All right. So we've just finished this 8 queens problem where we talked about what are the possible places of the queens that we can do, and then just recursively calling on each of the possible ways that I could get a solution from where I'm currently at. So I look at all the possibilities of where I could place a queen, and then just recursively call and eliminate all the squares for which I know I cannot place a queen once we do the recursion. And so that's what we do, and eventually if we run the algorithm long enough, we get a solution like this. There are many other solutions, but this is one of them that you'll get. So like for the first queen, we place it in the first square, then we eventually will find out that that doesn't work, so we try the second square, then the third, eventually we'll get to one that works. All right, so just analysis. So at each placing of the queen, we eliminate several squares. So it's actually quite, I tried to figure out what the complexity of doing this is, because when we did the brute force analysis, it's just place 8 queens anywhere on the board. That's just 64, choose 8. But here, if we look back at what the algorithm is doing here, so here we only eliminate 7 squares on the top row, 7 in the column, and 7 on the diagonal, so we eliminate 21 squares there. But here, I don't eliminate exactly 21 squares, right? I eliminate 5, not counting the ones that have already been eliminated, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 squares in this case, right? So it's different depending on which queen you have placed, and also what queens have already been placed, right? And also the position too. So the analysis of how many solutions I will be checking here is actually quite difficult to get right. So one thing that may be a possible project idea if you do other things is to figure out how many solutions really am I checking here. Or in general, if I have an n by n square grid of squares instead of just 8 here, and I want to place n queens on the board, how many solutions am I possibly going to generate doing this backtracking strategy? So that'd be a cool thing to figure out. So the first queen removed 21, and we know that the absolute minimum for the first queen is 21. It's just a simple exercise. If you move the queen somewhere else, you're going to be eliminating more squares. This reduces the running time, right? Because I'm removing all the solutions for which I know will not work because of doing this constraint satisfaction, which I'll define in a second, but I'm choosing only the squares for which I know will work. So we may have an exponential amount of time because I'm checking for each solution, which may have it might have 8 solutions or may have 2 or 3 solutions each. So it may do 2 to the n different possibilities here. So it still could be exponential here. But the good thing about doing it this way is we're going to be structuring it in an algorithmic way. There's a structure for finding solution if there is one. It's not just this haphazard try everything. We're actually doing this in an algorithmic way, which I think is the more important thing to do. So what is this constraint satisfaction thing? Well, by the title, it means that we have some constraints on the problem that we want to talk about, and we want to satisfy those constraints. So such that, like for the queens, we have the squares for which we know we can't place a queen. So we know that we can't place a queen in the same row column or diagonal as any other queen. So that's the constraint that we must satisfy for all queens here. When we place a queen, it has some limitations on where it can be placed. So what this is called is a constraint, right? We want to place the queen such that we satisfy the constraints. So we're going to be a little bit formal here, but it's basically a three-tuple, right? So we have XDC, so what are XDC? So X is a set of what are called variables. So X here is the set of queens. So those are the variables for our problem. D is the set of domains for what the values of these variables could be, of basically where the queens could be placed on the grid. So D will be 1, if we label each of the squares 1 through 64, the domain for each of the queens can be 1 through 64. Those are the places where I could possibly place each of the queens. And note here that the set of values for each of the variables could be different for each variable. But here it happens to be exactly the same. And C is a set of constraints. So each of the constraints is a subset of each of the variables. So I have a list of constraints, and each of the some set of the variables of X will be a part of each of the constraints. So what we call this is a constraint satisfaction problem, or CSP. So what it means to satisfy a constraint satisfaction problem is if we assign a value from D to each of the variables such that none of the constraints are violated. Or another way of saying that is we satisfy every single constraint. So let's just come up with the CSP for the 8 queens problem. So a variable, we can either assign it to each of the queens, but here we could formalize this a different way. So variables here could be the 8 rows, right? Because I must place exactly 1 queen on each of the rows. Because if I didn't, then I'd have a row with 2 queens, and that can't be allowed, right? So what do you think a value for each of the rows will be then? Well, what's a good idea for a value for each of the row? Well, it's going to be a value, some value. It could be true or false, but I'm not sure what true and false would correspond to. Well, it could be if I index each of the 8 positions 1 through 8 on each of the rows, it could be the number which is where I could place the queen. Okay? So here the domain will be 1 through 8. So these are the places where I can place a queen on each of the rows for each of the variables. So each variable has this domain of values 1 through 8, which will be for that row, the value of that row will be some value between 1 and 8, if we index the row that way. And then the constraints is we must have queens not on the same column or the same diagonal. So why did I not say row here? I'm already taking care of that in variables. Right, exactly. So I must have queens not in the same column or on either diagonal. So my variables are called x1 through x8. So let's just consider 2 variables, xi and xj. So the value of xi is where I placed the queen on row I, and for xj is where I placed the queen on row j. So what if they were in the same column? What would the value of xi and xj be? They must be the same, right? Because xi is the value of the column on row I, and xj is the column on row j. So if they're the same, then that means that they're on the exact same column, which we can't allow. So therefore, xi cannot possibly be equal to xj for every single pair of I and j, for every single pair of values, for every single pair of variables. And we can't have queens on the same diagonal, whether it be the main diagonal or one of the smaller diagonals in either way. So the way to formalize this is that the difference between xi and xj cannot be I minus j. So what this means is, let's just say that we placed a queen at the top left corner and another queen in the bottom left corner. So they are on the same diagonal. So what that means is xi, which will be x1 now, has a value of 1 because it's in square 1 of row 1. And the one for xj, which is x8, will be the value 8, right? So the row I is 1 and j is 8. So the difference between these in terms of the number of rows is 7, and the difference between them in the number of columns is 7. So we can't have the difference in the column number, the difference in the column number and the row number be the same, because that would mean that it's on the same diagonal. So xi minus xj, that corresponds to the difference in the columns. So xi minus xj is a particular value, which is the difference in the number of columns, and I minus j is the difference in the number of rows.
So change in x and change in y.
Yeah, exactly the same thing. They can't be the same number. Yeah, exactly. And this one, both of these work for basically both diagonals. So one diagonal will be the change in y is the same as the change in x, but the other one will be the negative of one of them will be the negative of the other. So we need two constraints there, but it's a minor point. But so now we have a set of constraints, variables, and the domain for each variable. So this is a constraint satisfaction problem. Any questions on 8 queens and how that works and how we formulated it as a constraint satisfaction problem? Okay, so another problem that's actually quite useful is called map coloring. So how many of you know about map coloring? Okay, so basically if you're given this partition of some kind of figure in the plane, so a partition is just dividing up the region into separate parts. So this is just a map of the United States, and so the partition is all 48 contiguous states here, right? And so what we want to do is, the map coloring problem says, let's assign a color to one of the states. Then every neighboring state that touches that state can't have the same color. So like an example for us, like Arizona is in red. So any neighboring state that has a non-empty boundary with Arizona, so it'll be New Mexico, Utah, Nevada, and California, none of those can have the color red. Okay? And then we try to figure out what is the minimal possible number of colors for which I can color the entire grid. And there's a famous theorem proved by, actually the only known proof of this theorem was by computers. It's called the 4-color theorem, which says that any plane partition, so anything where you can draw a partition like this in the plane, you can color in 4 colors or fewer. So I did it in 4 colors here, but it is possible that you can do less, but there's no possibility that this must have at least 5 colors by that theorem. So that's actually a really cool theorem, another project idea. So how do you think we can approach this problem from an algorithmic point of view? Well, let's just say that we're given this partition of a shape like the United States. Let's just call it a map. And so we say that 2 partitions, so like 2 states in the United States case, are adjacent if they have a non-empty boundary. And we want to assign each of these partitions, so each of the states, a color, such that no 2 adjacent partitions have the same color. That's what we want to do. So if we want to pose this as a constraint satisfaction problem, what we want to do is, the natural thing to do is, let a variable be each of the partitions, right? And so the states would be the variables in the United States case. For the domain is basically what values could the variables take on. So the values would be the colors that I can assign to each of the states or the partitions. So by the 4-color theorem, we can say that we only need 4 colors. So obviously, each state could be assigned any one of the colors. There's no restriction on what color it could possibly be assigned right now. It's just whatever color it could be assigned. So let's just say we have 4 colors, yellow, green, red, and purple. Those are 4 colors. And so the constraints are that if 2 partitions or 2 states have a non-empty boundary, then they can't have the same color. So if we have, for state I, let's just say C sub I is the color assigned to state I. And then so therefore, for every pair of states that are different, we can such that they have a non-empty boundary, then they can't have the same color, right? Because if they did, then that would violate what we were trying to do. We want to have adjacent states have different colors. So this is what this constraint is all about. Okay? So if we want to solve map coloring, the problem is that we could, although the four-color theorem says that four colors is sufficient, what if let's just say we had 3 colors, and we really did need 4 colors. So the problem is we could have too few colors, right? So the problem, what we can do is, what we can figure out is the largest possible number of neighbors for a given state. So let's just say that this number is D. So we can just use the number of colors, which is equal to the number of neighbors, right? Because if it's the largest number, then if we assign each of those other states that color, one of those number of states colors, then therefore we don't need any more than that, because it's the largest number, right? So if there is a coloring, if there is a way to color the map, and if we add more colors, we obviously could color the entire map, then every state must be a color. So doing this as a backtracking and constraint satisfaction approach is pick any random state and then pick any color, right? Because the starting color actually doesn't matter when I pick the first state, right? I could pick any one of those 4 colors for, say, Arizona. It didn't matter, right? All that matters is the neighboring states must have different colors, right? Pick any state, assign some color to it, and if there are any number of states with a given color, the given state that I want to color can't have any of those same colors. And if we can't assign to a particular state, say all the neighbors around it have 4 colors, all 4 of the colors, and I only have 4 colors, then I can't assign that state any color. So I must backtrack. So it's really a backtracking and constraint satisfaction approach. And then we just do a recursion on all the adjacent states that don't have an assigned color. So that's basically, so we're starting from a state, then expanding out until we reach the end of the map itself. Okay? So any questions on map coloring in general?
Can you go back
To the map, yeah.
You start with a color, and
Does
then
that-
go out.
Does that mean that map basically fails?
Oh, what do you mean fail?
Arizona, the colors are touching each other.
I thought that.
So I hesitated using the United States here. So that's
That's a special case.
yeah. So what that is how many of you actually been to the Four Corners there? So it's basically it's a pair of perpendicular lines. So for Colorado and Arizona, they're only on a corner. So it actually, I really wanted it to be non-empty for that reason. So if it had a nanometer in shared among the boundary, then I can't do this. But since it's on a corner, then I can't.
Okay, I was wondering, because when at first glance, it just seemed it looks like.
Right.
Yeah, I thought this was
Yeah. So yeah. Any other questions about? Yeah.
So in this case, you start with the state, like you said,
Mm-hmm.
expand out until you reach a problem, essentially.
Yeah.
Then backtrack.
Mm-hmm.
Does it matter where you start?
Nope. Because obviously, if there is a coloring, which I can use more colors, I can just start at any state and then do a branching out as before. It doesn't matter where I start because.
So there's an efficient way. Is there like a, say you started on May or something, would that be more efficient than say you're starting?
Not necessarily, because since it's like in a corner in a sense, if I started say from like California, I'm going to be hitting that corner anyway. So it doesn't matter if I start there or end there. There could be some efficiency in terms of just starting from the state that has the most number of neighbors, because I'll resolve any potential problems right away. So it might not affect the asymptotic running time, but it might affect the actual implementation running time. And it turns out this coloring problem is, we don't know if there's an efficient algorithm. And actually, we conjecture that there is no efficient algorithm to do this. Another project idea. So if you want to talk to me about a project idea about this, it's a really cool topic. So any other questions? All right, so we finished this map coloring part. So we have seen with 8 queens and with map coloring this kind of backtracking and constraint satisfaction problem approach. So let's do like what we did with brute force and try to see if there's like a general strategy for solving CSPs. So there seems to be some structure at random, like pick any random row, place a queen at some random position, or pick any random state, assign a random color. So here, just pick any variable at random because we have variables, domain, and constraints. Assign any value, right? Because I could be effectively trying every single value possibly, but so it doesn't matter what variable I assign any value to. And then I recursively call on all other variables assigned that are still unassigned, and then I try to assign them in recursion. And then consistent with constraints, that just means that I don't violate any constraints. So we recursively call on all other variables for which I still satisfy all the constraints. So let's just look at a general framework. So backtracking search with a particular problem, which I call CSP. This method, backtrack search, is just basically the handler for a method which will do all the recursion for recursively calling on when I pick a random variable with a random value. So it'll do the recursion for me. So let's look at this backtrack as recursive. So assignment will be the assignment to all the variables currently, and CSP will hold all the constraints that I want to check to make sure it's still consistent with everything. So if the assignment's complete, then therefore I must not have violated any of the constraints, right? So therefore I return the assignment that I made. So therefore we are done in that case. But if we're not, then there must be some unassigned variable, because if it's not complete, then there's some unassigned variable. So I choose any one, it doesn't matter which. So what I'm going to do is I'm going to look at every single value that I could assign to V. Because, as I said before, unlike the 8 queens and the map coloring problem, different variables could have different domains. So here, it actually may depend on the variable that I choose. So let's just say I have this magic method, which says, for this particular variable V, give me all the possible values I can give to it. And then what I'm going to do is I'm going to look at every single one of them. So value is going to be the particular value I'm looking at. So if this value is consistent with the assignment, so I'm not violating any constraints in this case, then I'm going to add to the assignment the variable set to this value, right? Because I'm looping through the values, and then I'm just assigning V to it if it is consistent with all the constraints. And then I'm going to recursively call on myself with this new assignment that I just added. And then if we have a result, which is basically what happens when I return from here when I say the assignment's complete. So result will be, if the assignment's complete, then I return the result that I have. Otherwise, if I get to a point where I can't assign a value anymore, then I remove this value from the assignment, and then I go back to the for loop, try the next one. Okay? And that's it. So I return none there because let's just say that this variable V, I can't assign anything to it. So therefore, I'm going to go through all its possible values, check every single one, do recursion on each, and for each one, I say no, it's not possible to assign that variable this value. So therefore, for all the other assigned variables, there must have been something wrong there. I can't get to this point for this variable. So therefore, I just say no. There was nothing I can do there, so therefore I must backtrack. Okay? So are there any questions about that?
If you were to really code this, you're gonna need like a list of what every state touches, right?
Yeah, so first of all, you'll need to know what are the possible values that could be assigned to each of the variables. Unless they're all the same, then it's more efficient. You'll need, so assignment here could be just a list of the values to each of the variables currently. And CSP could be a list of maybe like functions, which says if you look through every single possible constraint, you check if that particular assignment's consistent. So it could be just some magic method, but I'm abstracting details here. Okay. So any other questions? Yeah.
Real quick on the password checker, is a space a special character?
Yes, there's a space in the middle of some of them, but it doesn't count on the ends.
Yeah, because passwords on websites could allow for spaces. Yeah. Those,
So if they're on the end of it, so now.
oh, if they're on the end. Everything before the new line character.
Linear output is
Of course it
I
is.
didn't notice it with spaces.
Don't worry about it. Yeah, I'm not gonna really look at the test cases to make sure your program is exact, but it's just a good indicator. So I'll actually look at everything. Yeah, don't worry about it. So any other questions? So yeah.
On your code here, so I've noticed that sometimes Python allows things to be on the same line. Like you have if result, colon,
Mhm.
return result.
Yeah.
But sometimes it doesn't allow it on the same line.
Yeah.
Just kind of, is there like anything that shows like what you can put on the same line?
I've
And
tried.
is this a bad code?
I've tried to look, and I couldn't really find anything. So it's just to fit it on the slide here.
No,
but
no, I
yeah,
understand that. Yeah.
yeah.
I'm
So
saying in general, like, if you're not trying to minimize, is
Yeah.
it considered bad to start trying to put things on the same line?
yeah, I think so, because it's kind of the equivalent of in Java or C++ where you have like a if statement or a for loop, where you only have one thing in the if or for loop, and you don't have curly braces.
Yeah.
So basically, if you wanted to add another thing, you may want to just indent into it, but obviously it won't hit that line. But you avoid that with Python, but you can't really, if you do it on the same line, you can't really add another thing unless you can, but it's just not good practice. Because it's just harder to read sometimes. Yeah. So any other questions? So assignment 1's due tonight, and assignment 2 is due Monday, I believe. Okay?
You guys just like zip everything together in a folder or something?
Yeah, it says in the
Oh, yeah.
doc how to submit. Any other things? Okay, cool. I'll see you tomorrow.